So today we're going to finish talking about the Saha equation, and we'll talk about the HR diagram. So I'm going to start with the HR diagram, and then I'm going to go through, then I'm going to pick up the stuff that I didn't do last time. First, I'm going to talk about this collision thing. Okay, so there's a homework due Monday. Email me. I'm going to try again to check my email over the weekend. So if you get stuck on something, email me. It's not a super painful assignment set, but it's an astrophysics, so it's not free. Okay, so there's a reading due. There was a reading Wednesday, but I'm going to talk about it today. So let's see. So I'm actually going to go through old questions that I hadn't gotten to yet. So real quick, what's the difference between emission and absorption lines? So emission means that photons are coming out of the gas. So when you see a spectra, so say I've got a black body. If I have emission lines, then I have spectra that go, then I have light that goes up on top of my spectrum. And if I have absorption lines, I have dips in my spectrum. So an absorption line is where there's less photons than you think there should be, and an emission line is where there's more photons than you think there should be, for whatever value of you think there should be. So emission is easy to detect. So I can just have a very dark cloud that's spitting out some emission lines, and I'll see it. But absorption, there has to be a bright source behind it, and I have to know basically what that bright source is supposed to look like. Now for a black body, we know that it's smooth, so when I see a curve that looks like this, and I'll throw a couple of these up so that you can see what they look like. These dips are absorption lines. There are very few stars that look like black body with emission lines. That does happen, that they're a special kind of star. Yeah.
So when you see them on the spectra with the lines that you see in the rainbow, what do they look different on there, or do they look the same?
Yeah. Let me think if I've got. Let me just huck this
Actually,
image up.
The difference is very nuanced on that.
No, it's super obvious.
It's super obvious.
So this is what absorption lines look like in a spectrum.
Okay.
They're dark lines. An emission spectrum is the total opposite. So you would see black, except for a strong teal line here, and a strong blue line here, and a strong yellow line here. You just see black, except for that other stuff.
Okay, I think I've seen that.
That makes sense. So I don't have a good one with me, but it's just black with line in various spots. Okay, why are all these equations ratios? So this is kind of a simple question and kind of a very rich question. So on one hand, we need to make ratios because I don't know what the absolute number of hydrogen atoms is. It's large, but I don't actually care what the absolute number is. I only care about the fraction of, say, the second state relative to the first state. I need to normalize out the total mass of the star. So we use ratios to get rid of all the stuff that we don't care about. So that's answer one. And answer two is we can do two things. We can either write a distribution or we can write a ratio of two things. But a ratio of, like having a ratio of three things doesn't make sense. That gets complicated. And that has some implications that we'll talk about in a second. What's the significance of the letters O, B, A, F, G? Any more? Nothing. They have to do with the strength of the Balmer line, the way some dudes in Boston were thinking about them in the late 1800s. But now they don't mean anything. Now it's just the name of the star, like Bill or Tom or Jorge. It's just O, B, A, F, G now. There's probably a stellar astronomer that would disagree with me on that, but they're just the names of the stars at this point. And O is the most massive one, and M is the least massive, not the least massive star, but the least massive in that set. And it's related mostly to the mass. The mass is the key quantity that determines different spectral types. Where does this root mean square come from, and what's its significance? So let me talk about RMS for a second, just because that might be something that you guys haven't really seen much. So if I have a collection of particles in a bottle that's sitting on my desk, all of those particles are moving around like crazy, right? In the bottle. So say I just got air in a bottle, it's just an empty bottle with atmosphere in it. All of those particles are moving around like crazy. But what is the average velocity of the particles? What is the average velocity of a particle of water in my bottle here? 0. Because it's not moving. I mean, now it's moving. But when it's just sitting here on the desk, the average velocity is 0. How do I get the average velocity? I sum up all my VI's and I divide by the number. But when I add them all up, for every this way, there's a corresponding that way, because the average is 0. The whole bottle isn't moving. There's no mean motion. So if I want to talk about the typical velocity, I can't use the average velocity. So if I want to talk about the typical height of a kindergarten kid, I can use the average height of the kindergarten children, because that doesn't go to 0, that goes to 4 feet. If I want the average velocity, because it's a vector quantity, it's a signed quantity, that doesn't make as much sense. I'm going to get 0 when I average signed quantities. So instead, we average the square of the quantity. And then I have something that's in meters to the 4th seconds, or then I have something that's in meters squared, second squared, and that's not great. So I take the square root of that, and this is the root, that's this part, mean, that's this part, square, this part. This is the RMS velocity. And it's a way to measure the typical velocity of a thing that has 0 mean. There's a lot of additional things that go along with v squared. This also tells you the variance of the velocity distribution. This tells you how wide the distribution is. Yeah?
Why are we using this instead of like absolute value?
Absolute value is a pain in the ass to deal with, actually. So that's a really good question, because so that is a way a thing you can do. So I could also write absolute value, but absolute value is not an analytic function. I can't take a derivative of it. I mean, most of the places I can, but at 0, the derivative doesn't make any sense. So it's hard to deal with. I could raise this to the p, so in fact, we can do this. I can raise this to some number p, and then take the pth root, and then I have the p norm. So this is v, we write this as p. Doing the absolute value gives me the L1 norm, which is also a very useful thing to talk about. But it's not useful for characterizing. The square has the advantage that it tells me the typical velocity. It also tells me the width of the distribution. It also has all these other statistical properties that are handy, whereas the absolute value doesn't. But the absolute value is a useful thing to use sometimes. So that's a good question. Was that? It's mathematically awkward. And the square is less awkward. What is the partition function for? Okay, I am going to talk about the partition function. Oh, actually, I'm going to draw this thing so that I don't forget. Don't let me forget to talk about that. The partition function, I'm not actually going to talk about the partition function. I'm going to tell you what it is because it came up, but I don't need it. It's way too big a hammer for what I need right now for this class. But it's very cool and very powerful, so I'm going to talk about it because it's going to be confusing as Jesus when you get there when you get to StatMech. So let's talk about it real quick. The partition function z, it's always z. So remember this Boltzmann factor, e to the minus delta E over KT. This tells me the probability that I'm going to be in this one spot. It tells me the likelihood that I'm going to make this jump. I've got all this thermal energy kicking around. Some of that thermal energy is going to put me into a higher energy state. Why? Oh, now I'm going to talk about this.
Yeah.
Okay, let's not talk about that for a second. Let's talk about this for a second. Why does that put me in a higher energy state? So we say I've got two hydrogen atoms. And they collide. So remember in 2053 or 2048, I think, you did momentum and energy conserving collisions. So you remember doing P1 initial plus P2 initial equals P1 final plus P2 final. This is always true unless there's a force. And E1 initial plus E2 initial equals E1 final plus E2 final. Some of the time. When is the second one not true?
When there's a non-conservative force.
When there's a non-conservative force, when I have inelastic scatter. So this is plus the deformation energy. So if I have two cars, for instance, my initial momentum and my initial momentum of my two cars. So I have two cars, they're gonna hit each other, they're gonna bounce off. If they hit each other perfectly elastically, then momentum is conserved and energy is conserved. If they hit each other inelastically, momentum is conserved and energy is not conserved. So energy, the difference in energies so the total energy initial is the total energy final plus whatever energy you lost due to destroying the car. So the inelastic part is where that energy goes. And that's exactly what's happening when I have particles in a gas. And that's why we talk about this Maxwell distribution. So we talked about N of V dV equals V squared e to the minus V squared. I oversimplified here. I left out all the constants that I don't care about. I only care about the variable V. So this shape, this Maxwellian shape, tells us what the velocities are doing. And that's what we feed into problems like this. So we feed this velocity distribution into these two-body collisions. We don't actually do that. That's what nature does. So the deformation, so if I have two hydrogen atoms and they hit each other with, let's say they're both in the ground state, and we hit each other with delta E1, which is 13.6 times 1 over 2 squared minus 1 over 1 squared. This is the energy to kick one of these electrons into the upper energy. I really need two of that because everything's got to be symmetric, but that's all right. So let's just, so if I have this much energy is my relative energy coming in, then my relative energy going out might be 0, and they're both in the upper excited state. So they just hit each other, and if it's perfectly inelastic, then they will just bounce off with 0 velocity, but they'll both be in the excited electron state.
You said they have to be symmetric, so both have to be in the excited state?
No, I just realized that I was going to say something that was technically incorrect. Because you got two hydrogens, the state change rules are specific for reasons that I don't care about. So ignore that bit. You'll worry about that when you get to selection rules in quantum mechanics. So to go from this state to this state, you have to also inject the right amount of orbital angular momentum. So there's selection rules for going between states that I don't care about right now. So as long as these guys hit each other with enough energy to knock the electrons into the upper states, then they come out with less kinetic energy and they have more electron energy. So, does that make sense? So that's why I'm talking about these level populations. We have these things that are bashing into each other, and after they bash into each other, they come out of it with less kinetic energy, but they're excited. Yeah.
So do you have the exact wavelength for a photon going into like the first excited state? Is it, you're not going to lose any energy?
Yeah, so if you hit with, if two, so here we're not talking about photons. We're talking about atoms colliding with each other.
Okay, we were talking about photons and
Oh.
electrons.
Fascinating, I was talking about atoms. However, the same, oh no, maybe we were. I forget because we were talking real fast at the end, but I remember we were talking about momentum and energy. But the energetics is still the same. The basic idea is still the same. When I have a collision, sometimes it's inelastic, and I'll have and something will be in the different electron state. So an electron just has a kinetic energy if it's not in a bound state.
Oh, so the photon is just gonna bounce off of the atom?
Here, I don't
It
have any
doesn't
photons for a second. Let's forget about photons. Let's just talk about two atoms smashing into each other.
Okay.
And then we'll talk about photons in a second.
Alright.
So if we have just two atoms, that gets me excited states as well. So if they hit with exactly the right energy, then they will have zero relative kinetic energy coming out, but they'll both be excited if they hit just right. Does that make sense? So now we're also talking about photons. So there's a different process where we have photons in our excited state. So now I can just think about one of these guys. He's in the excited state because he just ran into this, and now he's got an electron in the upper excited state, and after a second, that electron will fall back down and give off a photon. And that's really the process that we're talking about the most. Most of the process is we're knocking two electrons off, it's jumping up into the excited state, and then it'll fall down and give us a photon. Now if I hit this thing, now if I have an electron in a de-excited state, and I hit it with a photon of, let's call this delta E1. This is like 10 electron volts, right? So let's say that this has exactly delta E1, and it hits this photon, then we'll have a similar momentum and energy kind of conservation problem to do. So I have a photon coming in and my hydrogen in the ground state. And then coming out, I'll have a photon with a different energy and a hydrogen in the first excited state. But it's the same momentum and energy conservation principles. I've got a P1, P2 who's got to equal P1, P2. Yeah.
So that incoming photon doesn't have to equal the exact energy?
It has to have enough energy.
It just has to have enough.
It has enough energy, and then either the photon scatters off, or this guy has all of the energy if it just absorbs the photon completely.
Okay.
So if they stick, that would be it hits it and they stick. Then that's in exactly the right energy state, and it won't go anywhere.
So what happens if you have enough to like go 2 energy states up? Like, is that like a selection thing, whether it goes 1 or 2 and bounces off?
There's quantum mechanics in the scattering and selection rules. So the state has to line up. So your orbit. So the angular momentum J going from here to here has to agree with the angular momentum of the photon that you pick up. So there are selection rules that way. I can't jump 2 with 1 photon because the angular momentum, unless the orbital has the right angular momentum. So don't worry too much about the details.
And that's in respect to the nucleus also. So it depends on the atom.
With the angular momentum?
Yeah.
Well, it's not really respect to.
Well, wouldn't it change the radius?
Yes, kind of. It changes the electron. It changes
Okay.
the state.
Okay.
So now we're getting into, we got to take quantum mechanics next. Now we got to talk about the partition function really fast. So we have these things that we can kick up into excited states, or they can fall down into unexcited states. So the probability of jumping up into one of the excited states is just this. It's just e to the energy that you need to get to over kT. So if I want to talk about all of the states, I have this thing called the partition function, which is the sum on all of the states possible, the degeneracy of that state, so how many electrons can I fit into that orbital or whatever, times e to the minus the energy of that state over kT. So here this is just the Boltzmann factor again. We're just summing up the Boltzmann factor for all of the possible terms. This thing is great because it describes all of the possible configurations for a system and how likely they are. It's also a magic machine that gives you stuff. If I take a derivative of this with respect to 1 over temperature, I get the average energy. If I take a derivative of this with respect to the temperature squared, I get the heat capacity. So this is a magic function that does all kinds of things, and I'm not going to say a single other thing about it. Take StatMech, and you will spend the whole time on this partition function. So it's very cool, but I don't need it, and the book doesn't really need it either, because you can just get away with the G's. But I wanted to say that just so that you didn't have giant mysteries, and you're going to see the partition function when you get to StatMech. What is partial ionization? So if I have, how many atoms are in a mole of hydrogen? Type 10 to the 20, 3. I don't care about the thing in front. The exponent matters. I'm an astronomer. The details don't matter. 10 to the 23, right? That's a lot. So when I have this state where I'm bunching things into each other, some electrons are going to come off and some aren't. So say 1% of my atoms are ionized, then I'll have a partially ionized gas where most of the gas is neutral, but some of them are ionized. Why does the Saha equation only work when things are in equilibrium? This is one of the dirty secrets of everything, and physicists assume things are in equilibrium all the time because then you can throw out the time derivative and then you can actually solve the problem. Doing things out of equilibrium is actually a really pretty rare selection of situations. Is when things are exploding or changing dramatically. And to deal with that, then you have to deal with a time dynamical system. So you can't throw out the time derivative, and everything gets a lot harder. So you don't see any non-equilibrium statistical mechanics or thermodynamics until you get to graduate school, and there's a reason for it. Why do we have to use statistics? Because astrophysics, physics, nature is a statistical process. Let's see, do atoms always stay in their ground state? Yeah, you can assume that everything's in the ground state unless you push it up. Because in 10 to the minus 10 seconds, they're all going to fall back down. The time for an electron to stay in an excited state isn't very long.
They don't like staying excited.
They don't like staying excited. It's very rare. The longest you can expect an atom to stay excited is like a second, and that's super long. Let's see. Part of the explanation of the Boltzmann sounded like it was a probability somewhere either 0 or 1, and that right? Yes. So this Boltzmann thing is a probability, and it goes between 0 and 1. It's not either 0 or 1. It's a continuous number between those two. Okay, and the rest of these are interesting questions that I'll come back to later. There's a couple others on the new reading that I want to talk about. My time management is going just fine. So what does it mean to scale an axis logarithmically? So I'll talk about this in a second when we talk about the HR diagram, but that's why I want to spend a second on this. So when I plot something, I have this stretch of space. This is 0 and this is 1. That's it. That's my graph. I have to map my data between this corner and this corner, which is 0 and 1 on my plot, right? So I want to make a plot that has all the luminosities of all the stars, and the luminosities of a big A star is 10 to the 38, or a big O star, and a G star is 10 to the 28. So I'm going to break my axis into ticks of a certain size. I want to represent both of these numbers. If these ticks are of the size 10 to the 38, then this number is down here and I can't see it. So are all the rest of them. So if this is 1 times 10 to the 38, and this is 2 times 10 to the 38, and this is 3 times 10 to the 38, and this is 7 times 10 to the 38, then I can't see any little numbers. So what I can do, though, is I can take the log of all the numbers, and then this one is just 38, and this one is just 28, and that's here and that's here. Those are easy to measure. So one thing we like to do is I don't want to plot the log of all the data. I want to plot it on an axis that's a log. So I don't call my numbers n times 10 to the 38. I say that this one is 10, and this one is 100, and this one is 10 to the 3, and this one is 10 to the 4, and this one is 10 to the 5, this one is 10 to the 7, this one is 10 to the 9. Now, okay, make these go up faster. Now you can represent much bigger numbers. So if I have 1,000,006, I can represent both 1,000,006 on the same graph. If I was doing a linear scale, I can't do that. So one of the funny things about a logarithmic scaling is multiplication turns into addition. And if I have something like p squared equals a cubed, okay, let's plot p versus a. So p goes like a to the 3 halves. So that's something like goes like kind of that, right? Now, if I'm going to compare two different populations and one goes like 1.5 and the other one goes like 1.6, I've got this slope and this slope. Those are really difficult to tell the difference. Like I can't tell if what this slope is versus this slope is curved. But if I take the log, if I plot them in a logarithmic axis, and I just logarithmically make these, this is what we did for homework. If I take the log of both sides of this, I'm left with log of p equals 3 halves log of a, and this is just a line. That's just a straight line, and I can tell deviations from a straight line pretty easily. So the other thing that this does is it turns power laws into lines. So making logarithmic axes makes power law things, where I've got something is related to something else to some power, which shows up all the time, turns that into a line. So logarithmic axes are the jam. And there's other kinds of axes that you can make. I like symmetric logs that go negative too. So you can't have a negative axis here. That's one of the problems with a logarithmic axis. Log of a negative number is imaginary. But you can tweak that in various ways. So can I explain spectral type? So the spectral type comes from the spectra. Actually, let me pull up my spectra. And where is it? Here. Here. So, and spectral typing is probably a little outside of the scope of the class in strong detail, but the important bits are the peak of the black body and what lines there are. So this is the spectra of several stars. So this is the flux that you get on Earth versus wavelength. And you can see that this one looks like it's peaking here. It's actually, it peaks around here. But the fact that this falls off is not the rest of the peak. There's actually extra stuff going on in here too. But you can see that the peaks of these shift that way, right? So from the peak, you can determine the temperature. And if you can't see the peak, you can measure the slope. So you can get the temperature, and you can get the spectral lines. And from that, they determine the spectral type, O through A. And then from the shape and the lines, the rest of these, the number shows up, the 5, the 7, the 6. I never care about those numbers, so I have a hard time retaining what they mean. And then the spectral class, which just shows how bright it is. So this is a spectrum. It doesn't tell you its luminosity. The luminosity information is gone. The absolute luminosity information is not in this plot. So we move to the HR diagram, which I'll now do. So the spectral type is somebody comes through and says, where's the peak of the emission? That gives you the main spectral class, A through M, O through M. The lines give you the second number, and how bright it is gives you the Roman numeral at the end. So we put this all together on a chart, and I'm trying to go on the thumbnails here. Where's the chart? I want to pull up the first one. Boop. And one of you said, so one of you looked at this and said, I see a lot of little dwarfy things. This point here is the only white dwarf on this chart. These guys are not white dwarfs. These are main sequence stars that happen to be dim. So what are we looking at? This graph has no axes. I would yell at this guy for not labeling these axes. So you got to label your axes, but that's all right. This was in the community, and everybody knew what he was talking about, and he talked about them. So the HR diagram is also called a color magnitude diagram. So an HR diagram is specifically B flux, right? Man, he doesn't say. I'm pretty sure it's the B magnitude. Let's just call it the total magnitude. H and R did it one particular way, and so an HR diagram is spectral class and visual magnitude. And the visual magnitude is a logarithmic function, right? Remember that? Because it's the log of the luminosity. And it's always written so brighter is up. So this is -5 and this is +5. So the axes are upside down number-wise, but up is brighter. And the spectral class is O, B, A, F, G, K, M in this axis, in that order. So that's the way that these guys, who had no idea what was going on, came at trying to get their head around what was going on. They were like, well, how do stars behave? Let's just put them all in one place and look at them. So we're going to compare the brightness and the spectral class, but we know now that spectral class is relevant to temperature. So I can write spectral class here. I can also write color here, B minus V. That says Y. Or I can write temperature. And temperature increases this direction, so hotter stuff is in that direction. Because, as I said before, Hertzsprung and Russell didn't know what was going on. And that's not a dig, it's just the state of science at the time. So they did it this way. But now we know that it's temperature going this way. And we have, so we can call this an HR diagram, or we can call it a color magnitude diagram, which is a more general, kind of diagram. But what it tells us is how bright a thing is and its temperature. And I know that the brightness, the luminosity, is A times some number times t to the 4th. Where A is, here, let's call this 4 pi r squared. So it goes like the radius of the star. So they had sorted that out. They also sorted out that the peak lambda is 2.9 millimeters over the temperature. And this sets the spectral class, or is related to the spectral class. So the spectrum comes from the spectrum, and the temperature comes from physics. So this relationship is very powerful. So that lets me write, if I'm thinking about things as terms of their spectra, O, B, A, F, G, or if I'm thinking about things in terms of their temperature, that's just temperature, and that increases that in that direction. And he put all the stars that he could find on this plot. And it's up there. Actually, I should change the camera. Camera is on the wrong thing. Hit. So we have this strip that goes like this. And there's a whole bunch of stars here. And we have a little population that's here. And these are white dwarfs. And we have a population here that are giants. And then we have a population up here that are supergiants. And this is called the main sequence.
So where are the red giants?
Up here. So,
Are there other colored giants?
yeah.
So
Was that?
Are all the colored giants in there?
Yeah.
Okay.
What sets the color on this graph? I wrote it down. What's that?
Temperature.
Yeah. Temperature determines the color.
Yeah.
That's B minus V. So blue is over here, and red is over here. And these are, this isn't cerulean and crimson. This is loosely bluish and loosely reddish. It's kind of an orange, and this is kind of a white. So blue giants are over here, and red giants are over here. So they're just on different spots of the giant branch. Okay, so let's look at a couple. So let's look at, this is Norris's first one, yeah.
Are dwarfs always white?
No. Everything on the main sequence is a dwarf.
Oh.
However, that's dumb, so we don't actually call them that. I mean, sometimes you'll hear the sun referred to as a G dwarf, which is accurate because it's on the main sequence. Everything on the main sequence is a dwarf. Everything that's not a giant is a dwarf. But we never call the main sequence stars dwarf stars. We call them main sequence stars. But by this dwarf or giant, they're all dwarfs. Yeah.
Can I say that the mass increases diagonally on this graph? Like, is that like a direct correlation? Is it, well, not perfectly diagonally, but like contour lines?
Okay. Not for all of them. For some of them, yes. So mass increases diagonally along the main sequence. But where does this star come from?
The main sequence.
It came from the main sequence. It came from over here. So these guys go up over here.
Yeah.
So what happens when a star dies? I'm going to spend a whole lot of time on how a star dies. But before it actually explodes, it runs out of fuel, and the mean entropy per baryon goes way up, and they expand like crazy. And when they expand, they go from something that's very small and very hot to something that's pretty big. What's the temperature do?
It decreases.
It goes down. I recognize that both answers are sensible because it got a lot bigger. It got a lot bigger because of the physics inside, not because it got hotter. It gets cooler, so it gets redder, but it gets brighter. So it goes from here, where it's hot and blue, it moves up as it gets brighter. It gets brighter because the radius increases. The luminosity is the radius squared temperature to the fourth. So the radius goes up, and the brightness goes up like a square of the radius. So that's pretty fast. So mass is increasing this way, but then I have a guy that has some mass here, and he ends his life, and he'll move up over here. But also, he'll shed a lot of mass in the process too, because there's winds and stuff. So,
Ends its life? Like, like what do you mean? Like main sequence life?
yeah.
Okay.
So stars stay on the main sequence until they can't burn hydrogen anymore. Once they burn hydrogen, then they start to blow up. And this is a very protracted explosion. And that's when they move over. So its life on the main sequence ends, and then it goes over here. And this is its end of life sequence. This is like hospice. That was kind of dark, I'm sorry.
Oh god, that was fun.
So,
Yeah.
That was funny. So over the course of its lifespan, can a star go from like white dwarf to supergiant?
Not in that direction.
Not in that direction? What?
White dwarf is the toilet. This is the bottom. So a white dwarf, so a star goes from here. From here, they explode and turn into neutron stars or black holes. From down here, they go turn into white dwarfs.
Okay, so white dwarfs are hospice and giants
No,
are
no,
hospice.
white dwarfs are a graveyard. Well, the white dwarf is a casket because the thing's already dead. Nothing else is happening to a white dwarf. It's going to sit there and cool for the age of the universe and just get cooler because there's no more nuclear burning going on in a white dwarf. There's no fire anymore. The fire's gone. Yeah.
Is something that determines whether it turns into a neutron star or a black hole, or is it kind of just statistical? Like,
Is it just the mass?
I would like you to ask that question of every astrophysicist you could find and collect how many answers you get.
Okay.
Because that's a super good question, but we actually don't know. So, okay, we know to an extent, as you go up in mass, the smaller things turn into white dwarfs, the bigger things turn into black holes or neutron stars. But which thing turns into a black hole and which thing turns into a neutron star? I would say that that science has no idea. Somebody who studies supernova will tell you a much more nuanced answer that says the same thing. Because it's very messy. It's very hard to tell when things are going to turn into a neutron star or a black hole. So that's a super open question. And people have answers, but I don't trust a single one of them. I don't believe it. Because it's too messy. It's too messy.
As of now, we can't know.
Yeah, as of now, we have no idea. So bigger things will turn into a black hole or a neutron star. Not a white dwarf, because a white dwarf would just get crushed and turn into a black hole from all this stuff. We'll talk about all those endpoints a little bit later.
So white dwarfs don't explode, they don't implode or anything, they just kind of rot.
Yeah, they're just cool, unless
Unless they feed.
they feed. And if it can feed, then it can explode.
So what does it eat?
Another star.
Oh, okay. So they're cannibals.
Yeah, yeah. And okay, which other star isn't clear? There's got to be another star. Maybe it's another white dwarf. I'll go through all the vagaries of white dwarfs later.
So can the giants feed too, or no?
Yeah, but they don't.
They don't. They don't want to?
Their density's low.
Okay.
So it typically you don't accrete mass once you're a big fluffy thing. So these big fluffy things are really low density.
Okay.
And usually you have a companion, and the companion's usually higher density. And the stuff, yes, that's actually a, sorry, as I start thinking about how to answer your question, it gets more interesting. So when most stars are binaries. I saw a really cool talk a couple of years ago where the guy stood up with a woman, stood up and said, all stars are binaries, and all binaries are triples. So most stars are in multiple systems. Not all stars, but easily half of all stars are in binary systems. So when I start off with a binary star, I have two stars, and they're on the main sequence. This guy then leaves the main sequence. This one is a lower mass star, so he doesn't leave the main sequence yet. But we just trust me on that one. This guy gets really big and fluffy and low density, and closer to this one. The gravitational potential for the gas out here is low. It's far away from the middle. So then the stuff is loosely bound here and can spiral into this guy. It doesn't go the other way. That's like rolling uphill.
So it feeds the smaller star?
Feeds the smaller star.
Alright, so that means the main sequence can also feed, but the supergiants don't?
I don't want to speak in too many absolutes, but yeah, generally. A main sequence star will feed. Supergiants don't get any more massive. They lose a lot of mass. They're in the process of losing mass.
That kind of makes sense because the gravitational potential is very low.
Yeah, that's right.
When it gets really big. Okay.
Where did my... Oh, wrong.
Sorry, we went
Just
down a rabbit hole there.
Yeah, it's all good. That's why I go through questions. I figure when I start questions, there's going to be a rabbit hole. So if I lose the whole day to just talking about those questions, that's cool. Let's see. Is there anything else that I need to say about the HR diagram? Do you guys have any other questions about it that I care to answer? Otherwise, I'm going to do, if you guys have 3 minutes, I'm going to finish up Saha. Yeah.
So do stars move upwards towards the supergiant range or diagonally?
They peel off diagonally from the main sequence. So it starts up here, and these guys go up, and then these guys go over here, and then these guys go over here, and then these guys go over here, and then these guys go over here. So you can tell how old a star cluster is by what the most massive thing is. I'll get into that a little bit later. Okay. Notes for the day. That is day 14. I need day 15.
We're gonna just grab on you.
Man. I'm glad I did Saha first. Or I did HR diagram first. It was a long time. Okay, I'm going to do this one integral that I half-assed because I was running out of time. The other day, that since this kind of physics is on the next homework set, or this math is on the next homework set, I want to do it. Okay, so I've got this integral 0 to infinity of 2hc squared lambda to the fifth over e to the hc over lambda kt minus 1 d lambda. And then we also have 4 pi squared r radius of the star squared.
Is it lambda the negative thing?
What? Yes. Good, good. Yeah, it's a fun game to check to spot my errors. There's plenty of them. So I do appreciate when you catch my minus signs. It's challenging to write things accurately and be telling a story at the same time. So I've got this 4 pi r squared that comes from the solid angle and the surface area integrals. And I'm not ever going to ask you to do those integrals again. Just remember 4 pi squared r squared. And then this bit, which I'm also not going to ask you to do, but I'm going to ask you to do other things that are just like it, so I want you to do that. So the integral that I told you was x cubed over e to the x minus 1 from 0 to infinity dx equals pi squared over 15. Is that right? Fourth. Pi to the fourth over 15. Doesn't really matter what that is. It's pi's and stuff that you need to get it right if you're going to compare to actual data. So we do a u substitution, and the u substitution is going to be, well, it has to be I have to make this exponential look like an x. So my u substitution has to be whatever is in here is x. I'm going to call it u. So u is hc over lambda kt. And then lambda, we'll just solve that. Lambda is hc over u kt. I find I always need to just do both when I'm doing a u substitution. And then du, I just take a derivative of this, thinking, okay, what's the derivative, what's the variable here? The variable here is lambda. So I'm going to actually, let me think about it this way. I'm going to take du d lambda, because that's my variable on the right-hand side. I can just say I'm going to take a derivative with respect to nothing, which is what I said the other day, and that's how I do it. But I'm going to think about it instead as du d lambda. So this is u, du d lambda is minus hc over lambda squared kt. Now I'm going to pull a physicist stunt and put this d lambda over here. Right? So I turn it from a verb into a noun, which is like magical thinking, but it works. And then I'm gonna solve for d lambda because that's actually what I want. D lambda is minus lambda squared kt over hc. The other thing I need to do, because I'm changing variables, is I need to change the limits of integration. So this limit goes from lambda equals 0 to lambda equals infinity, which is u equals infinity and u equals 0. So it switches the top and the bottom. So I need to introduce a minus sign to switch the limits of the integration. And that cancels out this minus sign here. Make sense? So now I'm left with, let's see, I got 4 pi squared r to the squared of the star times 2hc squared times, I got this d lambda, I'm going to have a kt over hc from that, and then this lambda stays inside the integral. I got lambda squared, lambda to the minus fifth, over e to the u minus 1 du. Did I get everything for my du? I got a kt over hc, so that's for my du. Now I got to get rid of these lambdas. So this is now lambda cubed. Oh, that's got to be the minus 3, right? Minus 3. So now I'm going to, oh no, that's plus. Sorry, I'm getting ahead of myself and trying to do the integral in my head before I get there. So this is lambda to the minus 3, because I had a lambda squared and a lambda to the minus 5. The lambda squared came from my Jacobian, that came from this thing here. So now I've got, let me write this nicely. lambda to the minus 3 over e to the u. Well, I got to get rid of this lambda by plugging in this u. And that u gives me an hc over kt, all this to the minus 3. Okay, and we can pull that outside. So now I got a kt cubed over hc cubed. Now I got a t and I got a t. This is my t to the 4th. That's where my t to the 4th comes from. And then on the inside, I've got u cubed over u e to the u minus 1 to u. And you got to take care of the h's and the c's and the k's, which you guys can do. But I wanted to make sure that I pointed out how to do the change of variables, where to make sure you don't screw up a minus sign, and where the t to the 4th comes from. And then this is just this function here, so I just drop in my pi to the 4th over 15. And I'm sorry. Several of these integrals on the homework. So if u substitution is not your favorite thing to do, now we will do some practice, and it will become your favorite thing to do. Or at least you'll get comfortable with it. Okay, homework due Monday. Email me questions. Oh, also bring questions. So the midterm is Wednesday. I will post all of the homework solutions in the next hour. Someone, if, was that?
Including the one due Monday?
Not the one due Monday. I like the way you think, and also you know that I'm a kind of a space cadet, so that might happen. Because I do have to write it so that I can post it immediately after I'm done talking about it.